Right now, Jupiter is so far away that if you started driving toward it at highway speeds the moment humans invented the wheel 5,000 years ago, you still would not be halfway there. The fastest bullet ever fired from a gun would need 50 years to reach Jupiter's orbit. The space between Earth and the fifth planet contains so much emptiness that every human who ever lived could float there without touching another soul. Yet this frozen gas giant, with its swirling storms and hidden moons, represents humanity's next great frontier. The journey to Jupiter reveals everything about our cosmic limitations and our technological ambitions. If unraveling the secrets of time and space fascinates you, tap like and subscribe. Your journey is just beginning. Let's begin. Open any diagram of our solar system. You will see neat circles showing planetary orbits arranged in tidy patterns. Mercury close to the Sun, Venus next, Earth in its comfortable position, Mars just beyond. Then Jupiter, sitting at a reasonable distance past the asteroid belt. These diagrams lie to you every single time. The actual distances between planets dwarf anything these simplified illustrations suggest. If we drew the solar system to true scale on a piece of paper, where Earth sat 1 inch from the Sun, Jupiter would need to be placed over 5 inches away. That sounds manageable until you realize that at this scale, Earth itself would be smaller than a microscopic bacterium. The planets become invisible specks floating in an ocean of white space. No textbook can honestly represent our solar system because human perception cannot process the true emptiness involved. Artists and educators face an impossible choice. Draw the planets large enough to see and the distances become meaningless. Draw the distances accurately and the planets vanish entirely. Every diagram you have ever encountered chose visibility over honesty. Consider what an accurate model would actually require. If you placed a basketball representing the Sun in the middle of a football field, Earth would be a tiny pebble smaller than a pea located about 26 yards away. Jupiter would be a marble sitting 134 yards from that basketball. But a football field is only 100 yards long. You would need to leave the stadium entirely just to place Jupiter correctly. And that marble representing Jupiter would still be too large for true scale. At this model size, Jupiter should be roughly the diameter of a small grape. Earth should be nearly invisible to the naked eye. The sun-sized basketball would be the only object in the entire model you could see clearly from any reasonable distance. This scaling problem reveals something fundamental about our cosmic neighborhood. The solar system consists almost entirely of nothing. Empty vacuum dominates every direction. The planets that seem so prominent in our understanding of astronomy occupy an infinitesimally small fraction of the space they orbit through. Jupiter orbits the Sun at an average distance of 484 million miles. Written with all its zeros, that number spans 12 digits. 484 million miles. Your brain cannot process this distance because evolution never required humans to comprehend such scales. We developed to understand distances we could walk, distances we could see, distances that mattered for survival on the African savanna. Nothing in human evolutionary history prepared us for 484 million miles. The number exists as pure abstraction, a sequence of syllables that conveys magnitude without triggering genuine comprehension. You can say the words. You cannot feel what they mean. Let me try to make this distance real. The circumference of Earth measures approximately 25,000 miles. A trip around our entire planet at the equator covers this distance. Now multiply that journey by 19,360. That is how many times you would need to circumnavigate Earth to equal the average distance to Jupiter. Still too abstract. Consider instead that commercial aircraft cruise at roughly 550 miles per hour. If you boarded a plane flying directly toward Jupiter at this speed and never stopped for fuel or maintenance, The flight would last approximately 100 years. You would die of old age multiple times over before arriving. Your grandchildren would die. Their grandchildren might finally glimpse Jupiter's cloud tops approaching through the cockpit windows. But this average distance tells only part of the story, because planetary orbits create constantly shifting relationships between worlds. Earth and Jupiter both orbit the Sun, but at dramatically different speeds. Earth completes its journey around our star every 365 days. Jupiter requires nearly 12 Earth years to complete a single orbit. This means the distance between our planets changes continuously as we chase each other around the cosmic track. Picture two runners on a circular track. One runner moves quickly, completing laps in just over a minute. The other runner plods along slowly, taking nearly 12 minutes per lap. Sometimes the fast runner catches up to the slow runner and they pass close together. Other times the fast runner is on the opposite side of the track, as far from the slow runner as the track geometry allows. Earth and Jupiter follow this same pattern on a vastly larger scale. At their closest approach, called opposition, Earth and Jupiter can be separated by roughly 365 million miles. At their farthest separation, when the Sun sits directly between both worlds, the gap stretches to approximately 601 million miles. The difference between closest and farthest exceeds 230 million miles. This variation matters enormously for space missions. Launch toward Jupiter when it sits on the far side of the Sun, and your spacecraft must travel nearly twice as far as if you waited for opposition. Mission planners obsess over launch windows, those brief periods when planetary alignments favor efficient trajectories. Miss your window, and you might wait years for the next opportunity. To understand what these numbers mean for actual travel, consider this comparison. Light itself, the fastest phenomenon in our universe, requires significant time to travel from Jupiter to Earth. When you look at Jupiter through a telescope tonight, you are seeing the planet as it existed in the recent past, not as it exists at this moment. The distance separating us creates a temporal gap that even light cannot instantly bridge. Human spacecraft move far slower than light. The fastest object ever launched by humanity reached speeds of approximately 330,000 miles per hour during its closest approach to the Sun. Even at this blistering pace, the journey to Jupiter would require weeks. Typical interplanetary spacecraft travel at fractions of this record speed, stretching Jupiter journeys across years. The vast majority of spacecraft travel at speeds between 20,000 and 40,000 miles per hour. At these velocities, reaching Jupiter becomes a multi-year endeavor that tests both technology and patience. 20,000 miles per hour sounds impressive until you do the mathematics. At this speed, covering 365 million miles requires over 2 years of continuous travel. Covering 600 million miles requires more than 3 years, and spacecraft rarely travel in straight lines. Orbital mechanics demand curved paths that often exceed straight-line distances by substantial margins. Consider the Pioneer missions, humanity's first ambassadors to the outer solar system. Pioneer 10, launched in March 1972, carrying instruments designed to study Jupiter's radiation environment and magnetic field. This spacecraft represented the cutting edge of 1970s technology, packed with scientific instruments that would provide humanity's first close-up data about the giant planet. The spacecraft took 627 days to reach its destination. Nearly 2 full years passed between launch and closest approach, 21 months of waiting while a small metal cylinder crossed the void between worlds. Scientists who celebrated the launch watched seasons change, holidays pass, and nearly 2 complete trips around the Sun before Pioneer 10 finally arrived at Jupiter. Pioneer 10 traveled a curved path through space, not a straight line. Direct routes between planets rarely make sense because spacecraft must fight against the Sun's gravitational pull, while also matching velocities with their targets. The Sun sits at the center of our solar system, exerting gravitational influence on everything that moves through its domain. The actual distance travelled by Pioneer 10 far exceeded the straight-line distance to Jupiter. The spacecraft followed a carefully calculated trajectory that balanced fuel efficiency against travel time. Mission designers traded directness for practicality, accepting longer paths because shorter paths would have required impossible fuel loads. Pioneer 11 followed in April 1973, reaching Jupiter in December 1974 after a journey lasting 606 days. Both Pioneer spacecraft used trajectories designed to maximize scientific return while working within the limitations of 1970s rocket technology. They also demonstrated exactly how long that reaching would take. The data returned by Pioneer 10 and Pioneer 11 transformed our understanding of Jupiter. These spacecraft discovered the planet's immense magnetic field, measured radiation belts that would prove deadly to unprotected electronics, and returned the first close-up images of Jupiter's swirling clouds. The scientific value of these missions justified every day of their 2-year journeys, but scientists and engineers wanted to do better. The Voyager missions demonstrated that faster journeys were possible with improved planning and more powerful launch vehicles. Voyager 1 launched in September 1977 and reached Jupiter in March 1979. The journey took approximately 546 days, shaving weeks off the Pioneer travel times despite launching years later. Voyager 1 carried more advanced instruments than its Pioneer predecessors. The spacecraft could study Jupiter's atmosphere in greater detail, image its moons with higher resolution, and measure magnetic fields with improved precision. But perhaps most importantly, Voyager 1 would not simply fly past Jupiter and continue into interstellar space. The mission was designed to use Jupiter's gravity to redirect towards Saturn. Voyager 2 launched actually before Voyager 1 in August 1977, but followed a slower trajectory designed to visit multiple outer planets. It reached Jupiter in July 1979 after 687 days of flight. The additional time allowed Voyager 2 to position itself for subsequent encounters with Saturn, Uranus, and Neptune. This grand tour trajectory represented one of the most ambitious flight plans ever conceived. Voyager 2 would visit all 4 giant planets in a single mission, using each planet's gravity to redirect toward the next. Such an alignment of the outer planets occurs only once every 175 years. The images returned by Voyager 1 and Voyager 2 at Jupiter stunned the world. Scientists saw the Great Red Spot in unprecedented detail, revealing a storm system larger than Earth that had raged for centuries. They discovered active volcanoes on the moon Io, the first volcanic activity ever detected beyond Earth. They found evidence suggesting that the moon Europa might harbour a liquid ocean beneath its icy surface. Each discovery emerged from spacecraft that had spent nearly 2 years crossing the void to reach Jupiter. The patience required for these missions produced scientific revolutions, but the travel times remained stubbornly long, despite the technological improvements incorporated into Voyager's design. The Galileo mission, launched in October 1989, faced unique constraints that extended its journey dramatically. Safety concerns following the Challenger disaster forced mission designers to abandon the originally planned trajectory. The alternative path required 6 years of travel, 6 entire years of humanity waiting while a school bus-sized spacecraft made its way to Jupiter through a series of planetary encounters. Galileo finally arrived at Jupiter in December 1995, entering orbit around the giant planet and beginning a mission that would revolutionize our understanding of the Jovian system. The extended travel time resulted from trajectory constraints rather than distance alone, demonstrating how mission circumstances can dramatically affect journey duration. The data returned by Galileo justified the long wait. The spacecraft deployed a probe into Jupiter's atmosphere, the first human-made object to sample the giant planet directly. It studied Jupiter's largest moons in unprecedented detail, confirming the existence of subsurface oceans on Europa. Galileo operated at Jupiter for 8 years, transforming a flyby into an extended exploration campaign. The Juno mission, currently orbiting Jupiter, launched in August 2011 and arrived in July 2016. 5 years of travel time, despite advances in propulsion and trajectory planning accumulated over decades of space exploration. Juno used an Atlas V rocket, one of the most powerful launch vehicles available at the time of launch, yet still required half a decade to reach its destination. Juno's mission focuses on understanding Jupiter's interior structure, its powerful magnetic field, and the auroras that dance around its poles. The spacecraft carries instruments that can peer beneath Jupiter's cloud tops, using microwave radiation, mapping the distribution of water and ammonia deep within the planet's atmosphere. The scientific questions Juno investigates required placing the spacecraft into a polar orbit around Jupiter. Every drop of propellant mattered because Juno would need substantial fuel reserves to enter Jupiter orbit and adjust its path during the primary mission. New Horizons holds the record for the fastest Jupiter arrival ever achieved. When it departed Earth in January 2006, the spacecraft was traveling at approximately 36,000 miles per hour relative to the Sun. This tremendous velocity carried it past Jupiter in just 13 months, dramatically faster than any previous mission. But this record comes with an important caveat. New Horizons never stopped at Jupiter. The spacecraft screamed past the giant planet, using its gravity to accelerate toward Pluto rather than entering orbit. 13 months represents the time required for a flyby, not for a mission that lingers to study the Jovian system. The distinction matters enormously for understanding what fast Jupiter travel actually means. Jupiter accelerated New Horizons by approximately 9,000 miles per hour, boosting the spacecraft toward its primary target in the outer solar system. The flyby provided an opportunity for bonus science observations while fundamentally serving as a gravitational slingshot. New Horizons gathered data during its brief encounter, but could not conduct the extended observations that orbital missions enable. The fundamental challenge of reaching Jupiter comes down to the basic physics of rocket propulsion. Spacecraft must carry all their fuel with them, and that fuel has mass that also requires acceleration. The mathematics of this relationship punishes ambitious missions severely. A spacecraft attempting to reach Jupiter quickly and then break into orbit would need fuel loads that exceed current launch capabilities by enormous margins. This constraint forces mission designers to seek alternatives to brute force propulsion. Gravity assists from other planets provide velocity changes without consuming onboard fuel. These gravitational boosts make outer solar system exploration possible, but they require trajectories that often add years to mission timelines. The physics of efficient travel rarely aligns with human impatience. The space between Earth and Jupiter contains almost nothing. This vast emptiness stretches for hundreds of millions of miles, with only occasional asteroid belt objects breaking the void. A spacecraft traveling this route might go weeks without passing within millions of miles of any significant mass. This emptiness creates both opportunities and dangers. Without atmospheric drag or gravitational perturbations, spacecraft can coast efficiently through the void. Engines fire only during course corrections or major maneuvers. The rest of the time, spacecraft drift ballistically, following paths determined by initial launch conditions and accumulated gravitational influences. But the same emptiness means no possibility of rescue if something goes wrong. A spacecraft that fails between Earth and Jupiter drifts forever through the darkness, unreachable by any conceivable rescue mission. No spacecraft currently exists that could catch up with the disabled Jupiter probe. The velocities involved exceed what any rescue mission could match. When the Galileo spacecraft experienced problems with its high-gain antenna, the antenna should have unfurled like an umbrella after launch. Instead, several ribs remained stuck, reducing the antenna's effectiveness by roughly 90%. No repair mission could reach Galileo. No astronaut could unfold the stubborn antenna. The spacecraft limped through its mission, transmitting at a fraction of planned capacity. The asteroid belt, often depicted in movies as a dense field of tumbling rocks requiring skillful piloting to navigate, presents virtually no obstacle in reality. Science fiction has trained audiences to expect a chaotic gauntlet of spinning boulders. The truth disappoints those seeking dramatic obstacle courses. The total mass of the asteroid belt amounts to only about 4% of Earth's moon. This modest amount of material spreads across a donut-shaped region more than 100 million miles wide. If you collected every asteroid in the belt and assembled them into a single body, you would have an object smaller than Pluto. Spacecraft routinely pass through the asteroid belt without incident. Pioneer 10 and 11 transited the belt with no problems. Every Voyager spacecraft passed through safely. Galileo, Juno, and New Horizons all crossed the belt without encountering any obstacles. The average distance between asteroids measures millions of miles. A spacecraft would need to aim specifically at an asteroid to have any reasonable chance of encountering one. The belt that seems so dangerous in science fiction poses no practical threat to Jupiter missions. Spacecraft pass through without even attempting to avoid anything. Mission controllers do not nervously monitor belt crossings. The supposed hazard is simply not hazardous, but the empty space itself creates challenges that take years to overcome. Without friction to slow them down, spacecraft maintain their velocities indefinitely. This means that initial launch conditions largely determine arrival times. Once a spacecraft leaves Earth, very little can be done to significantly shorten the journey without expending precious fuel reserves. Course corrections consume fuel that missions cannot afford to waste. Every kilogram of propellant used for trajectory adjustment is a kilogram unavailable for orbit insertion or other critical maneuvers. Mission designers calculate trajectories that minimize correction requirements, accepting longer paths in exchange for fuel efficiency. Mission controllers track spacecraft throughout their multi-year voyages, maintaining communication links across distances that strain the limits of radio technology. The vast separation between Earth and Jupiter creates communication delays that make real-time control impossible during critical mission phases. Spacecraft must operate autonomously, executing pre-programmed sequences without human intervention. A spacecraft entering Jupiter orbit must perform flawlessly on its own because help cannot arrive in time to matter. The confirmed record for fastest Jupiter arrival belongs to New Horizons at approximately 13 months. But this speed came at the cost of any ability to stop and study the Jovian system. For missions that actually want to orbit Jupiter and conduct extended scientific observations, 5 to 6 years represents the current realistic minimum. These timelines create practical limitations for Jupiter exploration. Scientific instruments must survive years of exposure to the space environment before beginning their primary missions. Cosmic radiation bombards spacecraft continuously throughout their journeys. Solar ultraviolet light degrades materials. Temperature cycles between sunlit and shadowed conditions stress mechanical components. Electronics must withstand cosmic radiation accumulated over multi-year journeys. High-energy particles from deep space can flip bits in computer memory, causing software errors. Radiation-hardened components resist these effects, but add mass and cost to spacecraft designs. Even hardened systems accumulate damage over years of exposure. Power systems must provide reliable electricity for more than half a decade before even reaching their targets. Solar panels degrade in the space environment. Radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity gradually lose output as their fuel depletes. Every system must be designed with margins sufficient to remain functional after years of pre-mission travel. And, for all the technological advances achieved since the Pioneer era, humanity has not dramatically reduced Jupiter travel times. The physics of rocket propulsion and orbital mechanics create fundamental barriers that engineering improvements can only partially address. We build better computers, more efficient engines, lighter structures. Yet the basic timeline for reaching Jupiter remains measured in years. This stubborn reality frustrates those who grew up watching science fiction, where spacecraft cross the solar system in days or weeks. Television and movies train generations to expect rapid interplanetary travel. The actual pace of space exploration disappoints these expectations repeatedly. Reaching Jupiter quickly remains one of the greatest challenges in human spaceflight. No breakthrough technology waits just around the corner to solve this problem. The physics involved has been understood for over a century. Improvements come incrementally, shaving months off multi-year journeys rather than transforming years into weeks. The distance to Jupiter serves as a humbling reminder of our cosmic isolation. This gas giant that appears as a brilliant point of light in our night sky floats so far away that years of travel separate us from its cloud tops. You can step outside on a clear night and see Jupiter with your naked eye. That bright, wandering star seems almost close enough to touch, yet reaching it requires patience, measured not in days or weeks, but in significant fractions of human lifetimes. Jupiter is practically next door compared to the outer solar system worlds beyond it. Saturn orbits nearly twice as far from the Sun as Jupiter. Uranus orbits 4 times farther. Neptune orbits 6 times farther. If reaching Jupiter requires 5 years, reaching Neptune requires decades. The Voyager 2 spacecraft launched in 1977 and did not reach Neptune until 1989. 12 years of travel to reach the 8th planet. Understanding how long it takes to reach Jupiter provides essential context for any discussion of human expansion into the solar system. These are not distances that can be crossed in days or weeks. These journeys measure in years, in significant fractions of human lifetimes. The time required to reach even our nearest giant planet challenges everything we assume about space travel from watching science fiction. A child born on the day Juno launched would have entered kindergarten before the spacecraft reached Jupiter. A graduate student proposing a Jupiter mission might retire before that mission returns its primary scientific results. The timescales of outer planet exploration exceed human career lengths and challenge institutional memory. But humanity continues sending spacecraft to Jupiter despite these challenges. Each mission teaches us more about the giant planet, its moons, and the broader dynamics of our solar system. The years invested in reaching Jupiter return scientific dividends that justify the patience required. And each successful mission brings us one step closer to the technologies that might someday make these journeys faster. The question is not whether we can reach Jupiter. We have proven that capability repeatedly over 5 decades of exploration. Pioneer, Voyager, Galileo, Juno, each mission demonstrated that human technology can cross the void between worlds. The question is whether we can ever make the journey quickly enough for human passengers to survive it. That challenge requires understanding the technology we currently possess and the limitations that still constrain us. Chemical rockets, gravity assists, ion engines, nuclear propulsion concepts that exist only on drawing boards. Each technology offers partial solutions while revealing new obstacles. The journey to Jupiter begins with accepting how long that journey truly takes, not the sanitized version from textbooks with their convenient diagrams, the real version where years separate departure from arrival, where spacecraft coast through emptiness far longer than any human has ever remained in space, where patience becomes the most essential resource for any mission attempting to explore the outer solar system. Jupiter waits. It has waited for billions of years and will wait for billions more. The giant planet does not care how long humans require to reach it. Only we care about that timeline. Only we feel frustrated by the years required to cross the void. Jupiter simply orbits, swirling with ancient storms, surrounded by moons that might harbour life, holding secrets we have only begun to discover. And every journey to unveil those secrets begins with accepting a simple, humbling truth. Jupiter is very far away. Getting there takes a very long time. No technology currently exists to significantly change that reality. The distance is real. The time required is real. And humanity must reckon with both before any human will ever see Jupiter's clouds from orbit. Every rocket that has ever carried humans into space operates on the same basic principle discovered centuries ago. Isaac Newton's third law states that for every action there is an equal and opposite reaction. Rockets expel hot gases in one direction and accelerate in the other. This fundamental physics has not changed since the first fireworks exploded in ancient China over 1,000 years ago. The Chinese inventors who created those early gunpowder rockets could not have imagined spacecraft traveling to Jupiter, but they would recognize the basic mechanism. Hot gases rush out of a tube. The tube moves in the opposite direction. Whether launching celebratory fireworks or interplanetary probes, the underlying physics remains identical. This unchanged principle should disturb anyone hoping for rapid progress in space travel. We have refined rocket technology enormously since those ancient Chinese experiments. We have replaced gunpowder with liquid hydrogen and liquid oxygen. We have engineered combustion chambers that withstand temperatures hotter than the surface of the sun. We have developed turbopumps spinning at tens of thousands of revolutions per minute to feed propellants into engines. Yet the basic mechanism, action and reaction, remains exactly what Newton described in 1687. Chemical rockets burn fuel and oxidizer to produce expanding gases that rush out of engine nozzles at tremendous speeds. The Space Shuttle main engines expelled exhaust at approximately 10,000 miles per hour. These engines represented the pinnacle of 1980s rocket technology, developed over decades at costs exceeding billions of dollars. Modern SpaceX Raptor engines achieve similar performance despite using different propellants and combustion cycles. These velocities represent the practical limits of chemical propulsion technology. 10,000 miles per hour sounds impressive, until you remember that reaching Jupiter requires sustained speeds of 30,000 miles per hour or more. Chemical rockets can achieve such speeds, but only by carrying enormous quantities of fuel that make spacecraft impractically massive. The energy available from chemical reactions has hard physical limits that no engineering can overcome. When hydrogen atoms combine with oxygen atoms to form water molecules, a specific amount of energy releases. This energy depends on the quantum mechanical properties of atomic bonds, not on human cleverness. No chemist can make hydrogen and oxygen release more energy than physics allows. Hydrogen and oxygen represent the most energetic practical rocket propellants available. Other chemical combinations release less energy per unit mass. Some exotic propellants like fluorine offer marginally better performance, but pose handling dangers that make them impractical for actual missions. We have essentially explored the entire periodic table searching for better rocket fuels. Hydrogen and oxygen remain the champions. This means we have essentially perfected chemical rocket engines to within a few % of their theoretical maximum performance. The Space Shuttle main engines achieved 99% combustion efficiency. Modern engines match or slightly exceed this figure. There is almost no room for improvement because we have already extracted nearly all the energy that chemistry permits. This perfection creates a ceiling on what chemical rockets can achieve. Imagine a car engine that already converts 99% of gasoline's energy into motion. You cannot make that engine dramatically more powerful by improving its efficiency. The fuel itself limits what is possible. Chemical rockets face the same constraint. To reach Jupiter quickly, spacecraft need to accelerate to tremendous velocities, then decelerate equally to enter orbit. The acceleration phase requires enormous energy. The deceleration phase requires equally enormous energy. Chemical rockets simply cannot carry enough fuel to accomplish both maneuvers in reasonable timeframes. Consider the mathematics of a direct Jupiter mission using chemical propulsion. A spacecraft launching from Earth already travels at approximately 67,000 miles per hour relative to the Sun. Earth's orbital motion provides this initial velocity for free. Every spacecraft launched from our planet inherits this tremendous speed simply by starting from a moving platform. To reach Jupiter orbit, that spacecraft must accelerate beyond Earth's orbital velocity, climbing outward against the Sun's gravitational pull. The required velocity, at Jupiter's distance, drops to roughly 29,000 miles per hour because Jupiter orbits more slowly than Earth. But reaching that slower orbit from Earth's faster orbit requires a complex transfer trajectory that temporarily accelerates the spacecraft to much higher velocities. The total velocity change required for a direct Earth to Jupiter mission exceeds 50,000 miles per hour when you account for both acceleration and orbital insertion. 50,000 miles per hour of velocity change. This number should terrify anyone familiar with rocket engineering. The Tsiolkovsky rocket equation, derived in 1897, describes the relationship between fuel mass, exhaust velocity, and achievable velocity change. This equation governs all rocket propulsion with mathematical precision that no engineering can circumvent. The equation reveals an exponential relationship between velocity change and fuel requirements. Doubling the velocity change does not merely double the fuel requirement. It increases fuel requirements exponentially in ways that quickly become impractical. For missions demanding high velocity changes, like direct Jupiter transfers, the mathematics become devastating. A spacecraft attempting to reach Jupiter quickly and then break into orbit would need to carry fuel masses exceeding 10 times the dry spacecraft mass. For a modest 1-ton probe, this means 10 tons of fuel. But that fuel also has mass that must be accelerated, requiring additional fuel to accelerate the fuel. The cascade continues until fuel requirements become absurd. Practical Jupiter missions using chemical propulsion would require initial masses in low Earth orbit exceeding hundreds of tons. No existing rocket can launch such payloads. The Saturn V, the most powerful rocket ever successfully flown, could place only 140 tons into low Earth orbit. A direct chemical mission to Jupiter would require multiple Saturn V launches just to assemble the fuel depot. This explains why no Jupiter mission has ever attempted a direct trajectory with chemical propulsion. The fuel requirements would make spacecraft impossibly massive and expensive. The physics does not care about human ambition. The rocket equation applies equally to NASA, SpaceX, and any other organization attempting interplanetary travel. Instead, mission designers exploit a technique that seems almost like cheating the laws of physics. Gravity assists allow spacecraft to gain velocity without burning fuel by stealing energy from planets themselves. This technique sounds like science fiction but relies on well-understood Newtonian mechanics. When a spacecraft approaches a planet, that planet's gravity accelerates the spacecraft. The spacecraft speeds up as it falls toward the planet, curves around behind it, and then slows down as it climbs away. From the planet's reference frame, the spacecraft arrives and departs at the same speed. No energy transfer seems to occur, but the planet is moving through space, orbiting the Sun at tremendous velocity. From the Sun's reference frame, the spacecraft can gain or lose speed, depending on whether it passes behind or ahead of the moving planet. A spacecraft passing behind a planet in its orbit effectively gets dragged along, departing with more velocity than it arrived with. The planet loses an infinitesimal amount of orbital energy in this exchange. Jupiter's orbit slows by amounts too small to measure when spacecraft steal energy from it. The giant planet contains so much orbital momentum that spacecraft extract energy like mosquitoes drinking from an ocean. Jupiter never notices the loss. The Voyager spacecraft used gravity assists from Jupiter to reach Saturn, then from Saturn to reach Uranus and Neptune. Without these gravitational boosts, the Voyager missions would have required either impossibly large fuel loads or vastly longer travel times. The grand tour of the outer solar system became possible only because gravity assists provided free velocity changes at each planetary encounter. Voyager 1 gained approximately 35,000 miles per hour from its Jupiter flyby. This energy boost would have required tons of additional fuel if generated by onboard engines. Instead, It cost nothing except careful trajectory planning. Jupiter's gravity performed work that chemical rockets could not economically accomplish. Voyager 2 executed an even more complex series of gravity assists. Jupiter redirected it toward Saturn. Saturn redirected it toward Uranus. Uranus redirected it toward Neptune. Each planetary encounter bent the trajectory and added velocity, enabling a mission that no chemical rocket could have powered directly. Juno demonstrated gravity assist efficiency using Earth itself as the boost source. The spacecraft's October 2013 Earth flyby added approximately 16,000 miles per hour to its velocity. Our own planet acted as a gravitational slingshot, flinging the spacecraft outward toward Jupiter without consuming a single drop of onboard propellant. But gravity assists come with costs that mission designers must carefully evaluate. They require precise trajectories that often increase total travel distance substantially. A spacecraft taking gravity assists from Venus and Earth might travel twice as far as a direct path to Jupiter. The extra distance translates directly into extra travel time. Gravity assists also depend on planetary positions that align only during specific launch windows. Planets orbit the Sun on their own schedules, indifferent to human mission planning. If Mars is not in the right position when you want to use it for a gravity assist, you cannot simply wait a few weeks. You might wait years for the next favorable alignment. The 1977 Voyager launch window exploited a rare alignment of all 4 outer planets. This configuration occurs only once every 175 years. Missing that window would have meant abandoning the Grand Tour concept entirely, or waiting until the 22nd century for the next opportunity. Launch window constraints add years to mission timelines even before spacecraft leave Earth. A mission designed around a 2025 launch window might be ready by 2023. The spacecraft then sits in storage, while engineers wait for planets to reach their required positions. This dead time inflates program costs and tests institutional patience. The Galileo mission exemplifies gravity assist complexity in its most extreme form. When the Challenger disaster forced abandonment of the powerful Centaur upper stage, mission designers faced a stark choice: cancel the mission entirely or find another way to reach Jupiter. They chose an elaborate gravitational pinball trajectory. Galileo flew past Venus in February 1990, stealing orbital energy from the second planet. The spacecraft then returned to Earth, flying past our planet in December 1990 and again in December 1992. Each flyby added velocity that Galileo's engines could not provide independently. This 3 gravity assist sequence demonstrates both the power and the cost of gravitational maneuvering. The flybys provided the energy a direct launch could not, but they tripled the travel time compared to what unlimited fuel would have permitted. Ion propulsion offers an alternative to chemical rockets that trades thrust for efficiency in ways that fundamentally alter mission architectures. Instead of burning chemical propellants in violent combustion reactions, ion engines use electric fields to accelerate charged atoms to extremely high velocities. The physics behind ion propulsion differs completely from chemical rockets. Atoms of propellant, typically xenon gas, pass through an ionization chamber where electrons are stripped away, creating positively charged ions. These ions then enter an acceleration chamber containing electrically charged grids. The electric field between grids accelerates ions to tremendous velocities before expelling them from the engine. The exhaust speeds from ion engines can exceed 100,000 miles per hour. Compare this to the 10,000 miles per hour achieved by the best chemical rockets. Ion engines expel propellant 10 times faster, which translates directly into 10 times better fuel efficiency according to the rocket equation. Higher exhaust velocity means more efficient use of propellant. Each kilogram of xenon expelled by an ion engine provides 10 times more momentum transfer than a kilogram of chemical propellant. Ion engines can achieve velocity changes impossible for chemical rockets of similar mass. The Dawn spacecraft demonstrated ion propulsion's capabilities during a mission to the asteroid belt. Dawn visited both Vesta and Ceres, the two largest objects in the asteroid belt, using ion engines for primary propulsion. This mission profile would have required impractical fuel loads with chemical propulsion. Ion engines made the dual asteroid mission possible. Dawn carried approximately 937 pounds of xenon propellant. Over its mission lifetime, the ion engines provided velocity changes exceeding 25,000 miles per hour. Achieving equivalent velocity change with chemical rockets would have required tens of thousands of pounds of propellant. Ion propulsion reduced fuel requirements by roughly a factor of 10, but ion engines produce minuscule thrust compared to chemical rockets. This thrust equals the weight of a few sheets of paper resting on your palm. You could easily overcome an ion engine's thrust by blowing gently on the spacecraft. This tiny thrust cannot overcome Earth's gravity or provide the rapid acceleration needed for quick planetary transfers. Ion engines work only in the vacuum of space where their gentle but persistent acceleration accumulates over months and years. No ion-powered spacecraft can launch itself from Earth's surface. All require chemical rockets to reach orbit before ion engines take over. The low thrust also means ion engines must fire continuously for extremely long periods to achieve significant velocity changes. The spacecraft accelerated slowly but relentlessly, gradually building the velocity needed to traverse the asteroid belt. A spacecraft using ion propulsion to reach Jupiter might achieve the journey with far less fuel than chemical alternatives. But the low thrust means the acceleration phase alone could require years. Ion propulsion trades speed for efficiency in ways that extend rather than shorten Jupiter travel times. Nuclear thermal propulsion represents the most promising near-term advancement for faster Jupiter missions. These engines operate on principles fundamentally different from both chemical rockets and ion engines. Instead of chemical combustion or electrical acceleration, nuclear thermal rockets use nuclear reactor cores to heat propellant directly. Hydrogen gas passes through a nuclear reactor, operating at extremely high temperatures. The reactor core heats the hydrogen to thousands of degrees, causing it to expand violently and rush out of the engine nozzle at high velocity. The exhaust speed exceeds chemical rockets because nuclear heating achieves higher temperatures than combustion. Nuclear thermal rockets achieve exhaust velocities roughly twice those of chemical rockets. This doubled efficiency translates into dramatically improved fuel economy, according to the rocket equation. A nuclear thermal mission to Jupiter could carry half the fuel of an equivalent chemical mission while achieving similar or better performance. NASA's DRACO program, developed in partnership with the Defense Advanced Research Projects Agency, aims to demonstrate nuclear thermal propulsion in orbit by 2027. The program name stands for Demonstration Rocket for Agile Cislunar Operations. If successful, this technology could enable Jupiter missions completing in under 3 years rather than 5 to 6. The improvement from 5 years to 3 years sounds modest when expressed as simple numbers. Scientists proposing missions would wait 3 years for results instead of 5. Institutional memory would more easily span the reduced duration. The improvement compounds across every aspect of mission, planning, and execution. Nuclear thermal propulsion was first tested in the 1960s during Project Nerva, the nuclear engine for rocket vehicle application. Engineers at that time achieved successful ground tests of nuclear rocket engines producing 75,000 pounds of thrust. These engines could have enabled crewed Mars missions by the late 1970s if development had continued. The Nerva program demonstrated that nuclear thermal propulsion works. Engines fired for extended durations at full power. Hydrogen propellant heated to design temperatures and exhausted at velocities exceeding twice chemical rocket performance. The technology was real, not speculative. Political priorities shifted after the Apollo program concluded. NASA's budget declined from its mid-1960s peak. Mars missions lost political support. Nuclear propulsion lost its primary justification and funding dried up. Decades of lost progress on nuclear propulsion now require rebuilding from nearly forgotten foundations. The engineers who developed Nerva have largely retired or died. Documentation exists, but institutional knowledge has evaporated. NASA must essentially restart nuclear thermal propulsion development from basic principles. The fundamental physics remain sound despite the lost decades. Nuclear reactions release millions of times more energy per unit mass than chemical reactions. A single gram of uranium undergoing fission releases energy equivalent to burning nearly 3 tons of coal. Harnessing even a tiny fraction of nuclear energy for propulsion could transform interplanetary travel. But nuclear rockets face regulatory and political challenges beyond engineering difficulties. Launching radioactive materials through Earth's atmosphere raises safety concerns that have prevented nuclear propulsion development for decades. No nuclear reactor has ever launched through Earth's atmosphere on an American rocket. What happens if a rocket carrying a nuclear reactor explodes during launch? The Challenger disaster spread debris across the Atlantic Ocean. A nuclear version of that disaster would spread radioactive material across potentially populated areas. The safety analysis for such events involves political calculations as much as engineering calculations. Solar electric propulsion combines ion engines with large solar panels to provide electrical power for the acceleration process. This approach works well in the inner solar system, where sunlight is intense. Spacecraft operating near Earth or Venus receive abundant solar energy that efficiently powers ion engine operation, but Jupiter orbits more than 5 times farther from the Sun than Earth. The intensity of sunlight decreases with the square of distance from the Sun. Moving from 1 astronomical unit to 5 astronomical units reduces solar intensity by a factor of 25. This dramatic reduction in available solar power cripples solar electric propulsion concepts for Jupiter missions. Ion engines require substantial electrical power to generate the fields that accelerate propellant ions. Without adequate power, ion engines cannot operate effectively. Solar panels that would enable rapid acceleration near Earth provide only feeble thrust at Jupiter distances. Juno demonstrated the limitations of solar power at Jupiter, while also proving it remains marginally viable. The spacecraft carries 3 enormous solar panels, each nearly 30 feet long. Together they span the length of a basketball court. These panels represent the largest solar arrays ever sent to the outer solar system. Yet Juno's massive panels generate only about 400 watts at Jupiter. Compare this to the thousands of watts they would produce near Earth. The reduced power suffices for Juno's science instruments and communication systems, but cannot support significant propulsion. Juno uses chemical rockets, not ion engines, for orbital maneuvers. Radioisotope thermoelectric generators provide an alternative power source that remains effective, regardless of distance from the Sun. These devices, commonly called RTGs, convert heat from decaying plutonium into electricity. The radioactive decay occurs continuously, whether the spacecraft orbits Earth or drifts through interstellar space. RTGs have powered every American spacecraft that ventured beyond Mars orbit. Pioneer 10 and 11 carried RTGs. Voyager 1 and 2 carry RTGs that continue operating nearly 50 years after launch. Galileo carried RTGs. Cassini carried RTGs. New Horizons carries RTGs. Without radioisotope power, outer solar system exploration would be impossible. But radioisotope generators produce limited power despite their reliability. A typical spacecraft RTG generates a few hundred watts, comparable to a few household light bulbs. This power suffices for communications, science instruments, and basic spacecraft operations. It cannot support propulsion systems requiring thousands of watts. The New Horizons flyby illustrates why raw speed statistics can mislead. That spacecraft reached Jupiter in 13 months but could not stop. Any mission intending to orbit Jupiter and conduct extended observations must carry fuel for deceleration. This breaking requirement transforms mission architectures entirely. The Europa Clipper mission, launched in 2024, will reach Jupiter in approximately 5.5 years despite using one of the most powerful rockets currently available. The mission could theoretically arrive faster with a more direct trajectory, but the fuel requirements would have exceeded what any existing rocket could launch. Even the SpaceX Starship, the most powerful launch vehicle ever designed, cannot overcome the basic physics constraining Jupiter access. A Starship configured for Jupiter might carry enough fuel to reduce travel time compared to current missions, but the improvement would be measured in months rather than years. Going from 5 years to 3 years represents meaningful progress. It does not transform Jupiter into a quick destination. The tyranny of the rocket equation becomes more oppressive with each increment of velocity demanded. Cutting Jupiter travel time in half does not require twice as much fuel. It requires many times more fuel in an exponential relationship that quickly exceeds practical limits. There are no chemical shortcuts to Jupiter. This reality check explains why decades of space exploration have not dramatically reduced outer planet travel times. The pioneer missions of the 1970s took similar times to reach Jupiter as the Juno mission of the 2010s. 40 years of technological advancement produced no breakthrough in transit duration. Computers became millions of times more powerful. Materials science produced lighter, stronger spacecraft structures. Solar panels increased efficiency dramatically. Communication systems handle higher data rates across greater distances. Nearly every spacecraft technology improved substantially. Travel times remained stubbornly unchanged. The technology we actually have for reaching Jupiter works. It is proven, reliable, and continues improving incrementally. Missions succeed with impressive regularity. Data returns exceed expectations. Scientific discoveries accumulate. But no combination of existing propulsion systems can deliver a spacecraft to Jupiter in weeks or months. The physics simply does not permit such rapid travel with current capabilities. Understanding these limitations provides context for evaluating claims about faster Jupiter travel. Any proposal promising dramatically reduced transit times must explain what new physics or engineering it employs. If the answer involves technologies that do not yet exist, the promise remains speculation rather than capability. The dream of rapid Jupiter travel persists despite these obstacles. Audiences raised on starships that cross galaxies in hours find chemical rockets embarrassingly slow. Multi-year transit times feel like technological failure rather than physical constraint. But wishing does not change physics. The laws governing propulsion care nothing for human expectations or narrative convenience. They apply equally to Hollywood spacecraft and actual NASA missions. Only the real missions must obey them. Yet humanity refuses to accept permanent limitations. Engineers and scientists continue developing concepts that might someday overcome the barriers constraining current missions. Laboratories investigate advanced propulsion physics. Theorists propose engines that current technology cannot build. These speculative systems range from extensions of proven physics to concepts requiring breakthroughs not yet achieved. The gap between current capability and theoretical possibility defines the challenge facing propulsion research. We know what physics permits. We cannot yet build what physics permits. Bridging that gap requires advances across multiple fields simultaneously. Engineering that transforms equations into hardware. The technology we actually have cannot send humans to Jupiter quickly. The technology we might develop someday could potentially achieve that goal. Between actuality and potential lies the work of generations. Every improvement in propulsion technology brings faster Jupiter travel slightly closer. Understanding current limitations provides essential context for appreciating future possibilities. The next section explores those speculative technologies that might someday overcome the barriers constraining present missions. These concepts range from physically plausible to wildly optimistic, all share the common characteristic of not existing yet as operational systems. In the 1950s, before any spacecraft had left Earth orbit, before Sputnik beeped its way into history, before humanity had proven that rockets could even reach space reliably, a team of scientists and engineers conceived the most audacious propulsion system ever seriously studied. Project Orion proposed propelling spacecraft using nuclear explosions. The concept sounds insane until you examine the physics. Then it sounds merely terrifying. The Manhattan Project had recently demonstrated that nuclear weapons released energy on scales previously unimaginable. The bombs that destroyed Hiroshima and Nagasaki converted tiny amounts of matter into city-leveling explosions. Scientists who had built these weapons began wondering whether the same physics could serve peaceful purposes. Could nuclear explosions push spacecraft instead of destroying cities? A nuclear bomb releases energy millions of times more concentrated than chemical explosives. A single kilogram of uranium undergoing complete fission releases energy equivalent to burning 17,000 tons of coal. If that energy could be directed to push a spacecraft rather than vaporize targets, velocities impossible for chemical rockets become achievable. The mathematics were undeniable, even if the concept seemed mad. The original Orion concept emerged from conversations between physicist Ted Taylor and mathematician Freeman Dyson at General Atomics in San Diego. Taylor had designed nuclear weapons at Los Alamos. Dyson had contributed to quantum electrodynamics. Together, they assembled a team that would spend years investigating nuclear pulse propulsion with full government funding and security clearances. Orion's designers calculated that nuclear pulse propulsion could carry humans to Jupiter in a single year, not 5 years, not 6 years, 1 year. The same technology could reach Saturn in 3 years, Pluto in a decade, and potentially achieve interstellar velocities given sufficient mission duration. Nuclear pulse propulsion offered performance improvements over chemical rockets, measured not in percentages, but in orders of magnitude. The Orion spacecraft would ride a series of nuclear explosions like a surfer riding waves. Small atomic bombs, each yielding roughly 1 kiloton of explosive force, would be ejected behind the vehicle at intervals of approximately 1 second. These bombs would detonate a few dozen meters behind the spacecraft, creating expanding plasma spheres that would slam into a massive pusher plate. The pusher plate formed the heart of Orion's design. This thick steel disc would absorb the nuclear blast, converting the explosive impulse into spacecraft acceleration. Behind the pusher plate, enormous shock absorbers would smooth the violent jolts into something human passengers could survive. Each bomb would provide an instantaneous kick. The shock absorbers would stretch this kick into a more gradual acceleration pulse. Thousands of bombs would propel the ship across the solar system. A mission to Jupiter might require detonating 300 nuclear devices. A mission to Saturn might require 800. Interstellar missions would require magazines containing tens of thousands of bombs. The spacecraft would essentially surf across space on a continuous series of nuclear fireballs. Detailed engineering studies demonstrated the concept's feasibility using 1950s technology and materials. Engineers calculated stress loads on the pusher plate. They designed shock absorber systems capable of converting millisecond impulses into second-long acceleration periods. They specified bomb designs optimized for propulsion rather than destruction. Test flights using conventional chemical explosives validated the pusher plate dynamics. Small-scale models demonstrated that explosions could indeed propel vehicles in controlled fashions. The physics worked exactly as calculations predicted. Orion was not science fiction dressed in engineering language. It was genuine engineering based on proven nuclear physics. Calculations showed that an Orion spacecraft could achieve exhaust velocities exceeding 100,000 miles per hour. Compare this to the 10,000 miles per hour achieved by the best chemical rockets. Orion offered 10 times better performance, translating into dramatically reduced travel times throughout the solar system. A crewed Orion vessel could reach Jupiter in approximately 12 months. The same ship could visit Saturn in 3 years and reach the outer solar system within a decade. Orion offered a pathway to rapid solar system exploration that remained technically sound if politically impossible. The solar system could have been open to human exploration before the 1970s ended. Freeman Dyson later reflected that Orion represented humanity's best near-term option for becoming a truly spacefaring civilization. The technology required no physics breakthroughs. It demanded only engineering development and political will. Nuclear bombs already existed in arsenals containing thousands of weapons. Repurposing some fraction of those weapons for propulsion seemed not only feasible but potentially beneficial. The original Orion designs ranged from modest to magnificent. The smallest version would have weighed roughly 4,000 tons, comparable to a naval destroyer. The largest designs exceeded 8 million tons, essentially nuclear-powered cities capable of carrying thousands of colonists to distant planets. Both extremes remained within engineering feasibility given sufficient resources, but Project Orion faced obstacles beyond engineering challenges. The Limited Test Ban Treaty of 1963 prohibited nuclear explosions in space, effectively ending the project before any flight testing could occur. The treaty aimed to reduce radioactive fallout from atmospheric nuclear tests. It also prohibited explosions in outer space, closing the door on nuclear pulse propulsion. Environmental concerns about radioactive fallout during atmospheric launch phases added further obstacles. An Orion spacecraft would need to climb through Earth's atmosphere using chemical rockets before beginning nuclear propulsion. But any launch failure would scatter radioactive bomb components across potentially populated areas. The safety analysis proved politically intractable. The technology that could have opened the solar system was abandoned before ever being flight tested. Government funding ended. The engineering team dispersed to other projects. Decades of potential development time evaporated. By the time engineers might have been landing nuclear-powered spacecraft on Jupiter's moons, humanity was still struggling to maintain space stations in low Earth orbit. Modern variations on nuclear pulse propulsion continue being studied, mostly by academic researchers with limited funding. The fundamental physics remains as sound as ever. Nuclear explosions still release tremendous energy. Pusher plates could still convert that energy into thrust. The technical obstacles that Project Orion solved in the 1960s have not unsolved themselves. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed using fusion microexplosions rather than fission bombs. Fusion releases even more energy per unit mass than fission, while producing far less radioactive waste. A fusion pulse drive would be cleaner and more efficient than Orion's atomic bombs while achieving even higher performance. The Daedalus study imagined a spacecraft propelled by igniting small pellets of deuterium and helium-3 using powerful electron beams. Each pellet would undergo fusion, releasing energy that would push against a magnetic nozzle rather than a physical pusher plate. The magnetic confinement would direct the fusion plasma rearward, providing thrust without the mechanical complexity of shock absorbers. Daedalus was designed for interstellar travel, targeting Barnard's star 6 light-years away. The study demonstrated that a fusion-powered spacecraft could reach another star system within a human lifetime, arriving at Barnard's star after approximately 50 years of travel. This timeline assumed technologies not yet developed but consistent with known physics. For a mission to Jupiter, such a spacecraft would be vastly overpowered. Daedalus could accelerate to 12% of light speed, far more than any in-system mission would require. A fusion pulse drive designed specifically for Jupiter could potentially complete the journey in weeks rather than months, approaching speeds of hundreds of thousands of miles per hour while carrying substantial payloads. But fusion propulsion requires solving fusion power generation first. This requirement has blocked fusion propulsion development for over half a century. Despite decades of research consuming billions of dollars across dozens of countries, sustained fusion reactions remain confined to laboratory experiments that consume more energy than they produce. Fusion powers the Sun and every other star in the universe. The physics is well understood. Hydrogen nuclei combine under extreme temperature and pressure to form helium, releasing energy in the process. Replicating this process on Earth requires heating hydrogen to temperatures exceeding 100 million degrees, while confining it long enough for significant fusion to occur. The ITER project in France represents humanity's most ambitious attempt to achieve practical fusion power. This international collaboration is constructing the world's largest tokamak, a donut-shaped magnetic confinement device designed to demonstrate net energy production from fusion. ITER aims to produce 10 times more energy than it consumes, proving that fusion power generation is possible. ITER hopes to achieve this milestone by the mid-2030s, but demonstrating fusion power generation is only the first step toward fusion propulsion. Converting a ground-based reactor into a spacecraft engine requires additional decades of development. Optimistic projections suggest fusion propulsion might become available by the late 21st century. Pessimistic projections suggest it may never prove practical. Antimatter propulsion represents the theoretical ultimate in rocket efficiency, the absolute maximum that physics permits within the constraints of known law. When matter meets antimatter, both annihilate completely, converting 100% of their combined mass into energy. No other reaction in nature achieves this perfect conversion efficiency. Chemical rockets convert less than 1/1,000,000th of their fuel mass into energy. The rest of the propellant mass simply gets expelled at relatively low velocity, wasting most of the material carried from Earth. Nuclear fission converts roughly 0.1% of fuel mass into energy, dramatically better than chemistry, but still far from complete conversion. Antimatter annihilation wastes nothing. Every particle of fuel converts entirely into energy that can be directed as thrust. The improvement factor over chemical rockets exceeds 1 billion. A spacecraft that would require millions of tons of chemical fuel could accomplish the same mission with grams of antimatter. A spacecraft carrying just milligrams of antimatter could generate enough energy to reach Jupiter in weeks. The exhaust velocity from matter-antimatter annihilation approaches light speed itself, limited only by the practical challenges of directing annihilation products. No other propulsion concept offers comparable performance potential. Antimatter propulsion would transform the solar system into a backyard. The catch, and there is always a catch in propulsion physics, involves producing and storing antimatter in quantities useful for spacecraft operations. Antimatter does not exist naturally in significant quantities anywhere humans have access. It must be manufactured using particle accelerators that consume enormous energy to produce tiny yields. Current antimatter production rates amount to nanograms per year across all the world's particle physics facilities combined. The cost of this production exceeds $100 trillion per gram when you factor in accelerator construction, operation, and the electricity required to run these massive machines. Antimatter is literally the most expensive substance in the universe. The entire world's cumulative antimatter production throughout all of history would not fuel a trip to the grocery store, let alone a voyage to Jupiter. We measure antimatter production in individual atoms, not in the grams or kilograms that spacecraft propulsion would require. The gap between current production and useful quantities spans many orders of magnitude. Containing antimatter adds another layer of impossibility to the challenge. Antimatter annihilates instantly upon contact with any normal matter. Storage containers cannot touch their contents. Antimatter must float suspended in perfect vacuum, confined by magnetic fields that prevent any contact with container walls. This magnetic confinement requires substantial equipment that adds mass to any spacecraft design. Antimatter propulsion remains theoretically sound but practically impossible for the foreseeable future. No realistic pathway exists from current capabilities to operational antimatter spacecraft. The physics works perfectly. The engineering remains centuries away, if it ever becomes achievable at all. Solar sails offer propulsion without any propellant at all, exploiting a phenomenon that seems almost magical until you understand the underlying physics. Photons from the sun carry momentum despite having no mass. This apparent contradiction resolves when you examine photon behavior through the lens of special relativity. Light exerts pressure on any surface it strikes. When sunlight hits a reflective surface, the photons bounce back, transferring twice their momentum to the surface. This pressure is minuscule by human standards. Standing in direct sunlight, you feel warmth but no push. Yet the pressure is real, measurable, and potentially useful for spacecraft propulsion. A sufficiently large sail could accelerate a spacecraft using nothing but sunlight pressure. The acceleration would be tiny, measured in fractions of millimeters per second squared, but this acceleration would continue indefinitely, requiring no propellant consumption. Over weeks and months, tiny accelerations accumulate into significant velocity changes. The Japanese Icaros mission demonstrated solar sailing in 2010, becoming the first spacecraft to successfully use sunlight pressure as its primary propulsion system. Icaros deployed a square sail measuring 14 meters on each side, roughly the size of a tennis court. This modest sail area proved sufficient to demonstrate controlled solar sail maneuvering in interplanetary space. Larger solar sails could achieve higher accelerations. A sail measuring hundreds of meters across could accelerate small payloads significantly faster than Icaros demonstrated. Kilometer-scale sails exist in engineering proposals that remain technically feasible if economically challenging. Such sails could potentially reach velocities that would carry spacecraft to Jupiter in reasonable timeframes, but solar sail performance decreases dramatically with distance from the Sun. The intensity of sunlight follows an inverse square law. Moving twice as far from the Sun reduces light intensity by a factor of 4. At Jupiter's orbit, more than 5 times farther from the Sun than Earth, sunlight intensity drops to less than 4% of its near-Earth value. A solar sail that accelerates well in the inner solar system becomes nearly useless approaching Jupiter. The sail continues functioning, but its acceleration drops by a factor of 25 or more. A spacecraft that gained velocity quickly near the Sun finds itself barely accelerating as it approaches its destination. Laser propulsion could overcome the distance limitation of solar sails by replacing sunlight with artificial illumination. Instead of relying on the Sun's relatively weak and diminishing light, a powerful laser on Earth or in Earth orbit could illuminate a sail with focused beams, maintaining intensity regardless of distance. The laser does not care how far away the spacecraft has traveled. A laser-pushed sail could potentially reach Jupiter in months rather than years. The beam would remain focused on the sail throughout the journey, providing continuous acceleration unavailable to solar sails in the outer solar system. With sufficient laser power, even crude spacecraft might achieve rapid interplanetary transit. The Breakthrough Starshot initiative proposes using powerful lasers to accelerate tiny spacecraft to 20% of light speed for interstellar missions. This concept envisions gram-scale probes pushed by ground-based laser arrays generating gigawatts of power. At 20% of light speed, these probes could reach the nearest star system in approximately 20 years. Scaled-down versions of this technology could enable fast Jupiter travel for small payloads. A laser array designed for Jupiter missions would require far less power than interstellar concepts. Probes weighing kilograms rather than grams could achieve velocities that would reach Jupiter in weeks. The physics is straightforward, even if the engineering is challenging, but no laser system currently exists with the power required for meaningful spacecraft acceleration. The Breakthrough Starshot concept requires laser arrays generating 100 gigawatts of power, roughly equivalent to the entire electrical generating capacity of a medium-sized country. Building such lasers represents a multi-decade infrastructure project, requiring investments measured in hundreds of billions of dollars. All of these advanced propulsion concepts share a common limitation that no engineering can overcome: they cannot exceed the speed of light. Einstein's theory of special relativity establishes light speed as an absolute cosmic limit. No matter how powerful the propulsion system, no spacecraft with mass can ever reach or exceed 186,000 miles per second. This cosmic speed limit emerges from the fundamental structure of spacetime itself. The faster you go, the more massive you become, the more energy required for further acceleration. Approaching light speed, mass increases toward infinity, while the energy required for acceleration increases likewise toward infinity. No finite energy source can accelerate any massive object to light speed. The barrier is not technological but fundamental. No matter how efficient your propulsion system, no matter how much energy you can generate, the speed of light remains forever out of reach for any object possessing rest mass. This cosmic speed limit creates a minimum possible travel time to Jupiter that no technology can reduce. At closest approach, Earth and Jupiter are separated by approximately 365 million miles. Light covers this distance in approximately 32 minutes. No spacecraft can ever complete the journey faster than 32 minutes regardless of propulsion technology. At maximum separation, when Jupiter and Earth occupy opposite sides of their orbits, the distance stretches to roughly 600 million miles. Light requires approximately 52 minutes to cross this expanded gap. These light travel times define the absolute floor for Jupiter transit duration that no future technology can breach. Of course, current and projected technologies remain nowhere close to light speed. Even the most optimistic fusion or antimatter proposals achieve perhaps 1% of light speed at maximum performance. The speed of light constraint does not limit present human capabilities, but does define ultimate boundaries against which all propulsion concepts must be measured. At 1% of light speed, approximately 1,860 miles per second, a spacecraft could reach Jupiter at closest approach in roughly 8 hours. At opposition, when Jupiter is farther away, the journey might extend to 12 hours. Such travel times would transform Jupiter from a multi-year destination into a day trip comparable in duration to a transoceanic flight. But achieving 1% of light speed requires propulsion technology far beyond current capabilities. The kinetic energy of a spacecraft traveling at 1% of light speed exceeds the kinetic energy of the same spacecraft at typical orbital velocities by factors of millions. Generating this energy and transferring it efficiently to spacecraft motion presents challenges that current engineering cannot address. The energy required to accelerate a crewed spacecraft to 1% of light speed exceeds the total energy consumed by human civilization in a year. Every power plant, every vehicle, every industrial process on Earth consumes less energy annually than would be required to push a single crewed spacecraft to such velocities. The energy barrier dwarfs any propulsion engineering challenge. More realistic near-term goals target velocities of perhaps 100,000 miles per hour. This speed remains far beyond current spacecraft capabilities but falls within conceivable engineering development over the coming decades. At 100,000 miles per hour, Jupiter at closest approach would require approximately 4 months of travel time. 4 months represents a dramatic improvement over current 5 to 6 year missions. The reduction transforms Jupiter from a career-spanning commitment into a challenging but conceivable mission duration. Scientists who propose missions might live to see results. Institutional memory would easily span the reduced duration, but even 100,000 miles per hour requires propulsion advances not yet demonstrated. The New Horizons probe, the fastest spacecraft ever launched, reached only about 36,000 miles per hour. Nearly tripling this record speed requires technologies still under development. The gap between theoretical possibility and practical capability defines the challenge of faster Jupiter travel. Physics permits spacecraft reaching Jupiter in hours or days. The equations balance. The energy exists in principle. Engineering and economics restrict us to years or decades because we cannot yet build what physics allows. Bridging this gap requires advances across multiple technological frontiers simultaneously. Better propulsion systems represent only part of the challenge. The entire spacecraft must evolve to accommodate faster travel. Faster spacecraft must survive higher accelerations that impose structural stresses exceeding current design limits. A spacecraft accelerating at 10 times Earth's gravity reaches high velocities quickly, but must withstand forces that would crush conventional structures. Materials science must advance alongside propulsion engineering. Faster spacecraft must maintain structural integrity at greater velocities, where impacts with space debris become more energetic. A grain of sand striking a spacecraft at 1% of light speed releases energy comparable to a small bomb. Shielding against such impacts requires mass that reduces the velocity advantages faster travel provides. The European Space Agency's Jupiter Icy Moons Explorer, launched in April 2023, will reach Jupiter in 2031 after an 8-year journey. This timeline reflects the practical limits of current technology applied within reasonable budget constraints. The mission uses chemical propulsion and gravity assists from Earth and Venus to reach its destination. No amount of clever engineering could significantly shorten this mission without fundamentally different propulsion. The trajectory was optimized using sophisticated computer simulations. The spacecraft design incorporates decades of engineering refinement, yet the travel time matches missions designed in the 1970s. Current technology has reached a performance plateau. Looking further ahead, NASA has studied concepts for faster outer planet missions using nuclear electric propulsion. These hybrid systems would use nuclear reactors to generate electrical power that feeds ion engines. The combination offers high exhaust velocity from ion propulsion with sustained power from nuclear generation, overcoming the solar intensity limitations that cripple ion engines at Jupiter distances. Nuclear electric propulsion could reduce travel times to Jupiter to approximately 2 years, cutting current mission durations by more than half. 2 years remains long by science fiction standards, but represents meaningful progress toward practical outer solar system access. The fundamental barrier to rapid Jupiter transit is energy. Everything in propulsion ultimately reduces to energy. Chemical rockets provide energy through combustion. Nuclear systems provide energy through fission or potentially fusion. Human civilization currently generates approximately 18 terawatts of power from all sources combined. This figure includes every power plant, every solar panel, every wind turbine, every nuclear reactor on Earth. 18 terawatts represents the total rate at which humanity converts energy into useful work. Accelerating a 1,000-ton spacecraft to 100,000 miles per hour requires energy equivalent to several hours of global electricity production. All the power plants on Earth running continuously for hours would be required to accelerate a single spacecraft to velocities that still fall short of rapid Jupiter transit. These energy requirements explain why proposed fast Jupiter missions always involve small robotic probes rather than crewed vessels. Reducing spacecraft mass dramatically reduces energy requirements. A probe weighing kilograms rather than tons might achieve high velocities, with energy requirements that future technology could plausibly provide. But crewed Jupiter missions cannot be reduced to kilogram scales. Human passengers require life support systems that process air, water, and food. They require habitation modules providing living space for journeys lasting months or years. They require radiation shielding, protecting against cosmic rays and solar particle events. The same physics that makes fast robotic probes possible makes fast crewed missions extremely difficult. The dream of rapid Jupiter travel persists despite these obstacles. Science fiction has trained generations to expect spacecraft crossing the solar system in days or weeks. The Enterprise visits alien worlds in single episodes. The Millennium Falcon crosses the galaxy in hours. These fictional timelines establish expectations that reality cannot satisfy. But physics does not care about expectations. The universe operates according to laws that no amount of wishful thinking can change. Light speed limits cosmic velocity absolutely. The rocket equation limits chemical propulsion inexorably. Energy requirements limit nuclear systems practically. These constraints are fundamental rather than temporary. What can change is human ingenuity applied to working within physical constraints. Engineers continue developing more efficient systems that extract greater performance from available physics. Each improvement accumulates toward capabilities that would have seemed magical to earlier generations. The first humans to reach Jupiter will travel using technologies not yet invented but consistent with known physics. They will face transit times measured in months if extraordinarily fortunate, employing propulsion systems still in laboratory development. More likely, they will face transit times measured in years, using technologies derived from current nuclear thermal or nuclear electric research. Sending robots to Jupiter requires solving engineering problems. Sending humans requires solving those same problems, plus keeping fragile biological organisms alive in the most hostile environment imaginable. The human factor transforms Jupiter missions from technically challenging to nearly inconceivable with current capabilities. Robots do not need food, they do not need water, they do not need air to breathe or space to exercise. They do not suffer depression from isolation or develop interpersonal conflicts with crewmates. Robots can be powered down during uneventful cruise phases and reactivated upon arrival. They can withstand radiation doses that would kill humans within hours. Every advantage that makes robotic exploration practical becomes a disadvantage when considering crewed missions. A spacecraft traveling to Jupiter spends years crossing the void between planets. During this transit, the crew remains isolated from any possible rescue. No spacecraft could be dispatched from Earth that would arrive in time to help a crew in distress. The fastest conceivable rescue mission would require years to reach a stricken vessel. Any emergency becomes a death sentence unless the crew can solve it using only onboard resources. Consider what this isolation means practically. A fire breaks out in the habitation module. On the International Space Station, crew can evacuate to a Soyuz capsule and return to Earth within hours. A Jupiter-bound crew has nowhere to evacuate. They must extinguish the fire using equipment they carried from Earth or die. There is no alternative. There is no backup plan involving external assistance. A crew member suffers a medical emergency requiring surgery. On Earth, ambulances arrive within minutes. Hospitals provide specialized equipment and trained surgeons. In deep space, the crew must perform surgery themselves, using whatever medical supplies they packed years earlier. If the surgery fails or the condition exceeds their capabilities, the patient dies. No medical evacuation helicopter will appear on the horizon. This isolation exceeds anything experienced in human history by orders of magnitude. Antarctic expeditions maintained the possibility of eventual rescue even during the harshest winters. Ships could reach stranded explorers within months when weather permitted. Submarine crews remain within range of surface support even during extended patrols. Radio contact enables coordination with rescue forces. Even astronauts on the International Space Station can return to Earth within hours, using emergency undocking procedures. Jupiter-bound crews would have no such options. The nearest help floats hundreds of millions of miles away. Radio messages require up to an hour for one-way transmission. By the time Earth learns of an emergency, the crisis has already resolved itself one way or another. The crew either solved the problem or died. Mission control can offer only delayed advice and moral support. The psychological stress of such isolation has never been tested on human subjects. We have no data on how humans respond to years of confinement with no possibility of rescue or early return. Every analogue we possess falls short of replicating the true conditions of interplanetary travel. The longest continuous human spaceflight lasted 437 days aboard the Russian Mir space station. Cosmonaut Valery Polyakov completed this marathon mission in 1995. demonstrating that humans can survive extended weightlessness without immediate physical collapse. But Polyakov knew that emergency return to Earth remained possible throughout his mission. He maintained regular communication with family and friends. He could see Earth outside his window. A minimum Jupiter mission using current propulsion technology would exceed 1,800 days. 5 years of continuous spaceflight. 5 years of confinement in volumes smaller than a typical apartment. 5 years of eating stored food, breathing recycled air, and seeing the same faces every single day. The mental health challenges of such extended isolation remain completely unknown. Soviet and Russian research on long-duration spaceflight provides glimpses into what crews might face, though these glimpses may underestimate the true challenges. Cosmonauts on extended Mir missions reported depression that deepened as months accumulated. Interpersonal conflicts erupted between crew members who had trained together for years and considered each other friends before launch. Cognitive difficulties emerged after months in space. Cosmonauts reported problems with concentration, memory, and decision-making. Tasks that seemed simple on Earth became frustratingly difficult. The combination of isolation, confinement, and physiological stress degraded mental performance in ways that ground-based training had not predicted. These problems emerged despite regular communication with Earth and the psychological comfort of knowing rescue was theoretically possible. Cosmonauts could speak with family members daily. They could watch television broadcasts from home. They remained connected to humanity. Even while floating above it, a Jupiter crew would face communication delays measured in tens of minutes to over an hour depending on planetary positions. Real-time conversations with Earth would be impossible. You could not call home and hear your spouse's voice responding to your words. Instead, you would record a message, wait an hour for it to reach Earth, then wait another hour for the response to return. 2 hours minimum between saying hello and hearing hello back. Video messages would arrive, showing family members as they appeared an hour ago. Your children would have aged by the time you saw their recorded smiles. Holidays would pass with greetings arriving hours after the celebrations ended. The psychological disconnect between crew and home would grow with every mile travelled toward Jupiter. Confined spaces amplify interpersonal tensions in ways that comfortable homes on Earth rarely demonstrate. Spacecraft interiors provide volume measured in cubic meters per crew member. The International Space Station offers roughly 400 cubic meters of pressurized volume for crews of 6. This sounds spacious until you realize it must contain all equipment, supplies, and workspace for everyone aboard. Privacy becomes almost non-existent in spacecraft environments. Crew members sleep in compartments barely larger than coffins. Personal space shrinks to whatever corner you can claim when others are not using it. Every conversation occurs within earshot of crewmates. Every argument becomes public. Every bad mood affects everyone aboard. Personal conflicts that might be minor annoyances on Earth become potential mission-ending crises when there is no escape from the people causing friction. On Earth, you can walk away from someone irritating you. You can go to a different room, take a drive, visit friends. In a spacecraft, you cannot escape. The person annoying you will be there tomorrow and the next day and every day for years. The Mars Desert Research Station and Antarctic research bases provide analogues for studying isolated crew dynamics. These simulations consistently reveal interpersonal challenges that mission designers must address before committing humans to multi-year space voyages. Crews that began simulations as friends sometimes ended as enemies. Professional relationships deteriorated under the stress of confinement. Crew selection processes for Jupiter missions would need to identify individuals capable of maintaining psychological stability through years of confinement with the same small group. This selection challenge may prove as difficult as any engineering problem. Humans are not designed for such conditions. Finding individuals who can thrive in them requires screening methods we have not yet developed. But psychological challenges represent only one dimension of human survival in deep space. Radiation exposure threatens crew health throughout any Jupiter mission in ways that current shielding technology cannot fully prevent. Earth's magnetic field and atmosphere protect surface inhabitants from the constant bombardment of cosmic rays and solar radiation. We live at the bottom of an ocean of air, beneath an invisible magnetic shield. These natural protections block radiation that would otherwise sterilize our planet's surface. We rarely think about this protection because we have never lived without it. Spacecraft lack this natural shielding. Once a vessel leaves Earth's magnetic embrace, its occupants face the full fury of the space radiation environment. This environment includes multiple threats that must be addressed separately. Galactic cosmic rays consist of atomic nuclei accelerated to tremendous energies by processes occurring elsewhere in the galaxy. Supernova explosions and other violent events fling particles outward at velocities approaching light speed. These particles travel through interstellar space for millions of years before some of them happen to encounter our solar system. Galactic cosmic rays pass through spacecraft hulls like bullets through paper. Aluminum shielding that seems substantial provides minimal protection. The particles simply punch through, depositing energy in whatever they encounter on the other side. When they strike biological tissue, they damage DNA and cellular structures in ways that accumulate over time. A single cosmic ray particle can shatter a DNA strand, causing mutations that may eventually produce cancer. The damage is random and cumulative. Each particle that penetrates the spacecraft adds to the total radiation dose absorbed by the crew. Over years of exposure, these doses accumulate to dangerous levels. A 3-year Jupiter mission would expose crews to radiation doses many times higher than the annual limits accepted for terrestrial radiation workers. Nuclear plant employees are limited to 5 rem per year. Jupiter crews might absorb several hundred rem over their mission duration. The health consequences include substantially increased cancer risk, possible neurological damage, and effects on cardiovascular systems that remain poorly understood. Solar particle events pose additional acute radiation hazards beyond the chronic exposure from galactic cosmic rays. When the sun erupts in major flares or coronal mass ejections, it releases floods of energetic particles that race outward through the solar system. These particles can deliver lethal radiation doses within hours to anyone caught without adequate shielding. Spacecraft crews would need heavily shielded storm shelters to survive major solar particle events during the years of transit. These shelters must provide enough protection to reduce acute doses below immediately dangerous levels. The crew might need to remain in shelter for days while the particle storm passes. The mass required for adequate radiation shielding conflicts directly with the mass limitations imposed by propulsion physics. Every kilogram devoted to shielding is a kilogram that propulsion systems must accelerate to Jupiter and back. Shielding that provides optimal protection might make the spacecraft too heavy to reach its destination. Beyond radiation, crews face physiological challenges from extended zero-gravity exposure that begin the moment the spacecraft leaves Earth orbit. Human bodies evolved under Earth's gravitational pull over millions of years. Every system in your body assumes gravity exists. Remove that pull, and systems calibrated by evolution begin failing in predictable but difficult to prevent ways. Bones lose calcium in weightlessness, at rates approaching 1 to 2% per month. The skeleton that supports your body against gravity becomes unnecessary without that gravity. Your body responds by reabsorbing bone material, weakening structures that Earth-bound humans depend upon. Muscles atrophy without gravity to work against. Your heart is a muscle that on Earth must pump blood upward against gravitational resistance. In weightlessness, this resistance vanishes. The heart weakens as it no longer needs to work as hard. Leg muscles that normally support your weight begin wasting within days of reaching orbit. Body fluids shift toward the head in weightlessness, causing changes that affect multiple systems. On Earth, gravity pulls blood and other fluids downward. Your body maintains fluid balance against this pull. In space, fluids redistribute upward, causing facial puffiness and more serious problems. Vision changes have affected many astronauts on long-duration missions. The fluid shift increases pressure within the skull, which in turn presses on the optic nerve and deforms the eyeball. Astronauts have returned from 6-month missions needing glasses for the first time in their lives. Countermeasures exist but require constant effort that consumes hours of crew time daily. Space station crews exercise 2 hours every day using specialized equipment designed for weightlessness. Resistance machines and treadmills with harness systems provide some of the loading that gravity normally supplies. Even with this effort, astronauts return to Earth significantly weakened after 6-month missions. They require assistance walking immediately after landing. Full recovery takes weeks or months. A Jupiter crew exercising throughout their years of transit would still face serious physical deterioration. Artificial gravity through spacecraft rotation could solve many physiological problems by recreating the gravitational loading that human bodies require. A rotating spacecraft generates centrifugal effects that push occupants outward, simulating gravitational pull. Science fiction has depicted rotating space stations for decades, recognizing that artificial gravity solves numerous health challenges. But rotating spacecraft add mechanical complexity that current engineering struggles to address. The rotation must remain stable throughout the mission. Solar panels and communication antennas must track their targets despite the rotation. Docking with other spacecraft becomes extraordinarily complicated when your vessel is spinning. The mass required for rotating habitats exceeds current launch capabilities by large factors. A rotating section must be large enough that rotation rates remain comfortable for human vestibular systems. Small radius requires high rotation rates that cause severe nausea. Large radius requires massive structural elements. Life support systems present another set of challenges, requiring years of reliable operation without maintenance, resupply from Earth. Air must be recycled continuously, removing carbon dioxide and replenishing oxygen. Water must be purified and recirculated. Food must be stored for years or produced on board through hydroponics or other biological systems. Current space station life support systems require regular resupply from Earth and significant maintenance by crew members. Consumables like filters and chemical cartridges arrive on cargo spacecraft every few months. A Jupiter mission cannot receive such resupply. A Jupiter mission would need closed-loop systems operating without external support for the entire multi-year duration. Every molecule of oxygen must be recycled. Every drop of water must be purified and reused. The systems must operate reliably for years longer than any life support equipment has ever demonstrated. Food presents particular challenges that closed-loop recycling cannot fully address. Freeze-dried and packaged foods have limited shelf lives. Vitamins degrade over time even in properly stored rations. Providing adequate nutrition for a crew of 4 to 6 people for 3 to 5 years requires either massive food stores or onboard production capabilities beyond current technology. Medical capabilities aboard a Jupiter-bound spacecraft must handle any emergency without resupply or evacuation. Surgical equipment, medications, diagnostic tools, and trained medical personnel must all be carried from Earth. The limited volume available cannot accommodate full hospital facilities. Some medical emergencies would simply be untreatable. Each challenge described represents a separate engineering problem, requiring solutions that do not yet exist at the required reliability levels. Combined, these challenges make crewed Jupiter missions impossible with current technology and uncertain even with technology projected for the next several decades. Yet Jupiter's moons provide scientific motivation that might eventually justify such difficult missions. The potential discoveries waiting in the Jovian system rank among the most significant questions science can ask. Europa, slightly smaller than Earth's moon, harbours a global ocean beneath its icy surface. This ocean contains more liquid water than all of Earth's oceans combined. Twice as much water as exists on our entire planet sloshes beneath Europa's frozen crust. Where there is liquid water, there might be life. Europa's ocean remains liquid, despite surface temperatures of -260 degrees Fahrenheit. As Europa orbits the giant planet, gravitational forces squeeze and stretch its interior. This flexing generates heat that maintains liquid water beneath the ice. Hydrothermal vents on Europa's ocean floor might provide energy and chemistry, supporting life forms entirely independent of sunlight. On Earth, communities of organisms thrive around deep-sea hydrothermal vents, deriving energy from chemical reactions rather than photosynthesis. Similar ecosystems could exist on Europa. If life exists on Europa, its discovery would rank among the most significant scientific findings in human history. Finding life that originated independently of Earth would prove that life arises readily when conditions permit. The universe would transform from a place where life might be a rare accident into a cosmos potentially teeming with organisms. This discovery would answer questions humans have asked since first looking up at the stars. Are we alone? Does life exist elsewhere? Is biology a cosmic commonality or an earthly peculiarity? Finding even simple microbes on Europa would revolutionize our understanding of our place in the universe. Ganymede, the largest moon in the solar system, also contains a subsurface ocean sandwiched between layers of ice. Callisto, another of Jupiter's large moons, may harbor liquid water as well. The Jovian system presents multiple targets for astrobiological investigation. The Europa Clipper mission will conduct detailed studies of Europa's ice shell, searching for plumes of water erupting through surface cracks. If such plumes exist, they would offer opportunities to sample Europa's ocean without drilling through miles of ice. A spacecraft flying through a plume could capture water molecules and analyze them for signs of life. But robotic missions face limitations that human explorers could overcome. Robots cannot adapt to unexpected discoveries with human-level flexibility. A robot programmed to search for specific chemical signatures might miss something unexpected that a human scientist would immediately recognize as significant. A human scientist on Europa's surface could investigate discoveries in minutes that might take robotic missions years to fully characterize. Finding something unexpected, a human could immediately devise new experiments, collect additional samples, and follow chains of evidence wherever they lead. This flexibility might prove essential for recognizing life forms that differ from our expectations. This scientific motivation drives continued interest in crewed Jupiter missions despite the technological barriers. Finding life on Europa would answer fundamental questions about humanity's place in the universe. The potential significance of such a discovery might someday justify the enormous investments required to send humans. The timeline for crewed Jupiter missions extends beyond confident prediction. Optimistic projections suggest the late 21st century, perhaps 70 or 80 years from now. Conservative estimates place human Jupiter visits in the 22nd century or beyond. Current technology cannot support such missions regardless of available funding. But technology changes in ways that confound prediction. Capabilities that seem impossible today may become routine for future generations. History provides repeated examples of such transformations. The Wright brothers' first powered flight in 1903 covered 120 feet in 12 seconds. The aircraft rose barely 10 feet above the sand. Skeptics questioned whether heavier-than-air flight would ever become practical for transportation. Within a human lifetime, aviation progressed from 12-second hops to global transportation networks carrying billions of passengers annually. Space technology could follow similar trajectories of improvement. Nuclear thermal propulsion might mature by mid-century, reducing Jupiter travel times to 2 or 3 years. Fusion power might become practical before 2100, enabling even faster transit. Advanced life support systems might achieve the reliability required for multi-year missions through decades of incremental improvement. The question of how long it takes to reach Jupiter has no single answer. The answer depends entirely on what technology you assume and when you ask the question. With current technology, the journey requires 5 to 6 years for orbital missions. This timeline has remained essentially unchanged since the 1970s, despite enormous progress in other space technologies. Chemical propulsion and gravity assists define a flaw that incremental improvements cannot significantly lower. With near-term nuclear thermal propulsion that might become available by mid-century, perhaps 2 to 3 years, this reduction would transform Jupiter from a career-spanning commitment into a challenging but conceivable mission duration. With advanced fusion systems that might emerge by the late 21st century, possibly months, fusion propulsion could enable Jupiter missions comparable in duration to historical ocean voyages. With theoretical antimatter drives that might never become practical, potentially weeks or days, such rapid transit would make Jupiter accessible in ways comparable to current intercontinental travel. But antimatter propulsion may remain forever impractical, regardless of technological progress. Each answer corresponds to different technological assumptions about what humans might develop and deploy. The physics of propulsion permits all these timelines. Energy can be converted to thrust. Mass can be accelerated through space. The equations balance for any assumed technology level. For now, Jupiter remains a destination requiring patience measured in years. Spacecraft currently operating at Jupiter took half a decade to arrive. Missions in development will require similar timelines. The giant planet that dominates our solar system floats so far away that even light requires nearly an hour to bridge the gap. This distance humbles human ambition while inspiring human determination. We have sent machines to Jupiter repeatedly, each mission returning knowledge that transforms our understanding of the solar system. Pioneer revealed Jupiter's radiation belts. Voyager discovered active volcanoes on Io and hinted at oceans beneath Europa's ice. Galileo confirmed those oceans and studied the Jovian system for 8 years. Juno continues revealing Jupiter's interior structure and atmospheric dynamics. We have not yet sent humans, but the desire to do so drives research programs across multiple nations. Engineers develop propulsion systems that might someday carry crews. Life support researchers pursue reliability levels that multi-year missions would require. The journey to Jupiter reveals the scale of our cosmic neighborhood in ways that challenge comfortable assumptions. If reaching a planet visible to the naked eye requires years of travel, what hope exists for visiting distant stars? If 500 million miles poses such challenges, what about the 25 trillion miles to the nearest star system? Jupiter serves as a testing ground for concepts that might someday enable interstellar exploration. Propulsion systems developed for Jupiter missions could scale to higher performance for missions beyond the solar system. Life support systems proven on Jupiter voyages could support generations-long interstellar journeys. The answer to how long it would take to reach Jupiter depends on when you ask the question and what technologies you assume. In 1972, Pioneer 10 required nearly 2 years. In 2024, Europa Clipper will require 5.5 years. In 2070, nuclear propulsion might enable 2-year transits. In 2200, technologies not yet imagined might make Jupiter a destination reachable in weeks. But today, in this moment of human history, Jupiter remains years away, regardless of how urgently we might wish to arrive. The gas giant, with its swirling storms and mysterious moons, floats at distances that demand patience from any explorer. We can see Jupiter with our naked eyes on any clear night. We cannot reach it within our attention spans. This gap between perception and accessibility defines the challenge of space exploration. The universe reveals itself to human observation while withholding itself from human presence. We map worlds we cannot visit. We study moons we cannot walk upon. We dream of voyages our technology cannot yet support. Jupiter represents both our cosmic ambitions and our present limitations. The 5th planet from the Sun hangs in our night sky as a reminder of how far humanity has come and how far we have yet to go. We have touched this distant world with robotic fingers. We have not yet touched it with human hands. Someday, perhaps within lifetimes already begun, Humans will stand on a moon of Jupiter and look back toward a blue dot barely visible against the sun's glare. They will know exactly how long their journey took because they will have lived through every day of it. They will have endured the isolation, survived the radiation, maintained their health through years of weightlessness. Until that day arrives, the question remains open. How long would it really take us to go to Jupiter? 5 years with current technology, 2 years with developing technology, months with advanced technology, weeks with revolutionary technology, days if we dream boldly enough and work long enough to transform dreams into engineering. The universe imposes no permanent barriers to human exploration, only current limitations we have not yet learned to overcome. Jupiter waits, as it has waited for billions of years, for the first humans ambitious enough and patient enough to make the journey. The distance is vast, the time required is long, but the destination is real, and someday we will arrive.